Hi-oh, here we are again, universal gravitation. Newton, as we know, had the big insight of the apple falling. As rumor has it, it fell on his head. Nothing could be further from the truth. He may have saw an apple fall, but it's doubtful that it fell on his head. He realized very simply from this action that the same force that makes that apple fall is the same force that makes any object orbit the Earth, including the moon. This is a big revelation for its time. He realized that the moon was being pulled down towards the Earth, but instead of hitting it, it kept missing. Think of it this way. If we keep going in a straight line on the Earth, we'll find that our straight line is really curved as the Earth curves around. But let's pretend that we couldn't curve, and we could actually leave the surface walking in a straight line. You'd find that curvature would be for every 8 kilometers or every 8,000 meters. The Earth would be 5 meters below your feet. So imagine, if you will, that you could travel horizontally those 8 kilometers. And we know from previously in the year, in 1 second, you will have fallen those 5 meters. In other words, if you did this, you would exactly match the curvature of the Earth. Every 8 kilometers out, 5 meters down. Taking a look at these pictures, you find if you go less, you're going to hit the ground. If you go more, you end up making an elliptical path around the Earth. But if you go just right, it makes a nice circular path. Newton imagined this idea thinking about a cannon on top of a mountain. He knew that the cannonball fired would hit the Earth. It would make a parabola. He knew if he hit it a little farther, it would go a little bit farther out. That parabola would have a wider base. And then he imagined, what if it matched it? He figured he would have to go those 8,000 meters in 1 second because he knew the object would fall 5 meters, the same curvature of the Earth. That was the revelation. It wasn't that gravity existed. Everyone knew gravity existed. What he realized was gravity was not confined to the Earth. It was merely universal. Everything, from the moon to the other planets to the farthest place you can imagine, was influenced by the gravity on Earth. From this, he created the law of universal gravitation. Although he didn't know exactly what the force of attraction was between two objects, he did know there was a relationship. And in fact, the mass was directly related to the force, but inversely related to the distance. It wasn't just as straightforward as that, because it turned out there was a squared relation. And this is called the inverse square law. The force is inverse, so 1 over, related to the distance, but it's the distance squared. So, under normal circumstances, you might say, if it's just inversely related, if we double the distance, then we have half the force. Or if we triple the distance, we have 1/3 the force. But we do need to square that. So if it's half the distance, you have to square that, and 2 times the distance, you have to square that, and it becomes 4 times the force. If it's 3 times the distance, you need to square it, and it becomes 9 times the force. Later on, it was experimentally determined, this big G. Big G is not to be confused with little g. Little g on Earth is -10. But big G is a constant. This doesn't change. Whether you're on the Earth, the moon, it doesn't matter. As long as we put this in, everything would work out. We'll get an absolutely known force. A little cartoon, remembering that all things have mass, and therefore all things have a gravitational pull. I find you more attractive than usual. You do? Is it my new haircut? Actually, I think it's all the weight you've been putting on. Your gravitational pull is pretty severe. Just saying. So true, though. So let's look at this quantitatively. We know our formula is F equals big G m1 m2 over d squared. We have a situation here, two quarry trucks. They each have a mass, and they sit 4 meters apart. So what's the force of attraction? Well, big G is 6.67 times 10 to the negative 11. That was a constant. Not to be confused with little g. One of the trucks is 7.521 times 10 to the fourth. The other truck is 7.521 times 10 to the fourth. And all of that is divided by 4 squared. And when you solve that out, you get 2.358 times 10 to the negative 2, or 0.02 newtons. Not very much. But if we look at this qualitatively, no math, we have to think of this as a balance. And so if we were to double one of the masses to keep our teeter-totter level instead of falling to the side, we have to put something on the other side. We put 2 over on the right, so 2 needs to be put on the left. In other words, we would double the force. What if we double 2 of the masses? Well, 2 times 2 is 4, so we've multiplied things by 4 times on the right. We must have 4 on the left. 4 times the force. But remember, the distance is a little different than the mass, because it's a squared relationship. If we increase the distance, the force of attraction decreases. So it's not half, but 1/4. And if we go the other way, we made this smaller, therefore the other side gets bigger. Bigger by the square of that. So it's 1/4 becomes 16 times greater is the force. What if we put it all together? Well, the force is going to triple. Then it's going to double that, which is 6 times. This is going to cause, the distance is going to cause it to be 4 times, right? We made this smaller, so the force gets bigger. 4 times. So 6 times, and then 4 times that would be 24. 24 times the force. How can we put this together? We have universal gravitation and Newton's second law. Well, they're both the same force, so when we put them together, MA will go over here. And of course, 1m will cancel, so the acceleration caused by gravity is big G m over d squared. And then it very much follows the same rules as before. So let's take a hypothetical situation. Let's suppose we could dig a hole through the center of the earth. What would happen if you fell through? Well, some simple thought will yield you the answer. If you're standing at the surface, you're being pulled and will accelerate with g. But as you fall down, you have less mass below you pulling you. And you're going to be pulled with less. And when you get to the middle, you're being pulled in every single direction. In other words, you're going to be weightless. So what's going to happen is, as you accelerate less and less as you get to the center, as soon as your inertia takes you past, you're going to slow down, because now you're being pulled backwards, and you'll make it to the other side, and you'll just end up oscillating back and forth.